What if you could understand quantum physics? In this video, we are going to break down what superposition is. A chair seems to be a chair. A coin seems to be heads or tails. A light seems to be on or off. In ordinary life, everything feels settled, solid, final. But deep under that familiar layer of experience, nature appears to work in a very different way. What if the world is not built from tiny objects that always have definite properties, but from possibilities that remain open until interaction forces an outcome? In this video, we are going to strip away the mystical language, the exaggerated metaphors, and the pop science confusion, and look at what superposition actually means. Superposition is one of the central ideas in quantum mechanics, and despite how strange it sounds, the basic structure is not nonsense at all. It is a scientific description of how physical systems behave before a measurement locks them into a specific result. Quantum mechanics emerged in the early 20th century because classical physics kept failing at very small scales. Light did not behave exactly like a simple wave. Atoms did not radiate energy the way older theories predicted. Electrons in atoms seemed to occupy allowed patterns rather than arbitrary ones. The old picture of nature, which worked extremely well for planets, projectiles, and engines, started to break down when scientists looked closely at matter and radiation. Experiments kept pointing in the same direction. Tiny systems did not behave like miniature billiard balls with neatly defined properties at all times. Instead, they behaved according to a mathematical framework that predicted probabilities with extraordinary precision. One of the clearest scientific clues came from the double-slit experiment. When particles such as electrons are sent toward a barrier with two narrow openings, the pattern on the screen behind it does not look like two simple piles, as if each electron chose one slit like a tiny pellet. Instead, under the right conditions, it forms an interference pattern, the kind usually associated with waves overlapping. Even more striking, this pattern still emerges when electrons are sent one at a time. That does not mean the electron is secretly doing magic. It means the best scientific description before detection is not "it went through this slit" or "it went through that slit" in the normal classical sense. The system evolves as a combination of possible states, and those possibilities affect the final probabilities we observe. That is the doorway into superposition. Superposition does not mean everything is literally everything, or your thoughts create reality, or the universe is just imagination. It means that a quantum system can be described as a combination of multiple possible measurable states at once, before a specific measurement outcome is obtained. The cleanest way to think about it is as a menu of possible answers with mathematical weights attached. Not a menu in your mind, a menu in the physical description of the system itself. Imagine a musical chord instead of a single note. A classical object is more like one note played clearly. A quantum state in superposition is more like a chord containing several notes at once. But when you perform a measurement, you do not hear the whole chord as separate classical outcomes laid side by side. You get one result. The mathematics tells you how likely each note was to be the one that emerges from that interaction. Another useful metaphor is a map. In ordinary life, we are used to a pin already being at one location. In quantum mechanics, before the relevant measurement, the system is more like a map containing several weighted destinations. The map is real in the theory. The final pin is what appears when the interaction selects an outcome. This is where people often get confused. They imagine superposition as a particle being physically smeared in the same way fog fills a room. That can mislead you. Superposition is not just fuzziness caused by ignorance, like not knowing whether a card is face up or face down. It is not merely a lack of information about a hidden classical state. Quantum mechanics treats the combined state itself as fundamental, because that combined state produces measurable effects such as interference. If it were only ignorance, the math would behave differently. The experiments would behave differently. The interference would disappear in situations where scientifically it remains. Another important point is that superposition depends on what you are measuring. A system can be in a superposition relative to one property and not another. For example, an electron can be in a superposition of spin states relative to a certain measurement direction. That does not mean all properties become meaningless at once. It means the structure of the state depends on the basis, the physical question being asked. That sounds abstract, but the basic idea is simple. Nature does not always store answers in the yes or no form we expect before we ask a specific kind of question. Measurement, then, is not just passive looking. In quantum mechanics, measurement is a physical interaction between systems. Something couples to something else. Information becomes encoded. A previously delicate quantum combination gives way to a definite outcome from the observer's perspective. That does not require human consciousness. A detector is enough. A screen is enough. An interaction with the environment is often enough to destroy the fragile conditions under which superposition shows itself clearly. This leads to another essential concept, decoherence. Decoherence is one reason we do not see obvious quantum superpositions in everyday objects, like footballs, dogs, or coffee mugs. Large systems interact constantly with air, light, heat, surfaces, and countless microscopic disturbances. Their quantum possibilities become entangled with the environment so quickly that the interference effects effectively vanish from ordinary observation. The world starts to look classical, even if quantum rules still underlie it. So superposition is not a sign that science has failed. It is part of why science succeeds. Quantum mechanics has predicted results with astonishing accuracy. Superposition is not a poetic add-on. It is built into the working structure of the theory. Without it, we would not understand atomic behavior, chemical bonding, semiconductors, lasers, MRI technology, or quantum computing. Quantum computing is especially interesting because it uses superposition in a controlled way. A classical bit is either 0 or 1. A quantum bit, or qubit, can exist in a superposition of 0 and 1 until measurement. That does not mean it is magically doing every computation at once, in the cartoonish sense people sometimes claim. But it does mean quantum systems can process information using interference and state evolution in ways that differ fundamentally from classical machines. The power comes not from mystical infinity, but from carefully engineered quantum structure. If all this feels uncomfortable, that is actually a reasonable response. Superposition challenges the mental habits we built for surviving at human scale. Our brains evolved to track rocks, faces, motion, danger, shelter, and social cues. We did not evolve to intuit the deep behavior of electrons. Expecting quantum mechanics to feel natural is like expecting a fish to understand aviation on first contact. If superposition is real, then one implication is that certainty may be less fundamental than possibility. The sharp world we experience may be a stabilized surface emerging from deeper probabilistic rules. Another implication is that measurement is not a trivial act. Gaining information is part of the physical story. The line between what is happening and what can be known is more tightly connected than classical intuition suggests. It also means that reality is not obligated to match everyday language. Terms like location, path, or state may still work, but only if we use them carefully. The deeper we go, the more ordinary words become rough approximations. A practical implication is psychological. Human beings often want the world to be either simple or magical. Superposition is neither. It asks for a more disciplined mindset, one that can tolerate uncertainty without collapsing into fantasy. That matters far beyond physics. In life, we often force premature certainty because ambiguity feels uncomfortable. Quantum theory does not tell us to become vague. It teaches us that precision sometimes begins with admitting that reality is subtler than our first picture of it. And maybe the deepest implication is this: the world is not less real because it is stranger than common sense. It may be more real precisely because it refuses to shrink into the categories that made us comfortable. Superposition is not about particles making a joke out of logic. It is about the scientific discovery that, at the quantum level, physical systems are described by structured possibilities that remain combined until interaction produces a definite result. That is not nonsense. It is one of the clearest signs that reality is deeper than appearance. The world looks fixed because we live at the scale where outcomes have already settled. But under that settled surface, nature may still be written in possibilities first and certainties second. Lucid Order. Question everything.